Welcome back. So let's continue where we left off. So we had this intuition that I must have something to do with these sign changes, right? The pattern of the sign changes of I are very similar to the pattern of the sign changes in the Maclaurin representation of cosine of x plus sine of x. And then we also saw that the i's, whether they're positive i's or negative i's, correspond to the sign terms. So let's do a little experiment. And it's not an experiment because I know where this leads to, but it could have been an experiment. What is e to the ix? E to the ix. Well, raising anything to the I power really isn't defined. I mean, when I itself was created by a definition, we said I squared is equal to -1 by definition. So I is a bit of a definition. So if we haven't defined what something to the ith power is yet, we really don't know what to do with it. But let's just say, for the sake of, that we can treat I just like any other number. And we do know what happens with I when you put it into a polynomial. That's one thing we do know. In fact, that's one of the reasons why I was defined in the first place, was so that people could take roots of all polynomials, even ones that didn't have real roots. So what happens if we take e to the ix? Well, I don't know what that is, but we know we could put that into the Maclaurin representation of e to the x. And actually, since you're taking my leap of faith that is equal to e of x, and all of its derivatives are equal to e to the x's derivatives at x equals 0, it's not that hard to imagine. And actually, you could plot the graph of this, and you'll see that they're identical. But anyway, so if we take the Maclaurin representation of this, everywhere where we see an x, we just replace it with an ix, right? So that will be 1 plus ix plus, so what's, well, let me just write it, plus I squared x squared over 2 factorial, I squared x squared, plus I to the third x to the third over 3 factorial, plus I to the fourth x to the fourth over 4 factorial, plus I to the fifth x to the fifth over 5 factorial. I don't have to keep going. Plus, and it just keeps going, right? So what happens when you simplify that? So that equals 1 plus ix. What's I squared? That's -1, right? Minus x squared over 2 factorial. And what's I to the third? That's minus I. So it's minus I x to the third over 3 factorial plus I to the fourth. So what's I to the fourth? That's just 1 again. So we get plus x to the fourth over 4 factorial. And then we have, what's I to the fifth? Plus I times x to the fifth over 5 factorial, right? And it just keeps going. But we have something interesting here. Now all of a sudden we have something extremely similar to this, except for only one difference. Right? Compare that to e to the ix. Compare that to e to the 8th. And the dots on my eyes always get merged. Compare these two things that I'm circling. What's the difference? Let's see, the 1, 1. Well, here I have an x. I have an ix here. The minus x squared over 2 factorial. So these terms are the same. Then on the x to the third, the signs are right, but I have an I. And then x to the fourth over 4 factorial, that's identical. But then on x to the fifth, I have an I. So the only difference between this and this is on the terms that involve sine of x, right? So what are the terms that involve sine of x? It's this term corresponds to that term, right? This term corresponds to that term, right? These are the terms that correspond to sine of x in this representation. That term corresponds to that term. And the only difference is, so this has all of the terms that the sine of x would have, but they all have an I in front of them, right? Even the sign is right? This is negative, that's negative, but this just has an I in front of it. So it turns out that you could rewrite this, right? You could rewrite this representation. Well, it doesn't turn out. It's pretty obvious you could rewrite it. Let me clear this just so we get a. So we could actually rewrite that e to the ix And we could write it, we could separate out the imaginary terms, and we could separate out the real terms. What were the real terms? Well, the real terms were 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and it just kept going to infinity, right? Those were the real terms. And then that's to infinity dot dot dot. No, this pen tool doesn't look, it looks like minus signs. I don't want to do that. Edit, undo, edit, undo, edit, undo, edit. Oh, I can't undo it. Anyway, so this is just dot dot dot, right? You can say plus dot dot dot. So those are the real terms essentially. And then the imaginary terms, it was plus, well, all of these terms are going to have I on them, right? So let me just take the I out. So plus I times, and we figured out that those terms were x, and they were the terms that minus, well, I don't want to give it away too fast, x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And it just kept going on and on to infinity, right? Well, isn't this the Maclaurin representation of cosine of x? And similarly, isn't this the Maclaurin representation of sine of x? Well, yeah, sure. And I mean, you probably realize in the previous screen where I showed that all of the imaginary terms correspond to the sine of x terms. And all the real ones, likewise, were the cosine of x when we said that, when we compared it to sine of x plus cosine of x. So if you believe me that the Maclaurin representation of e to the x is equal to e to the x, and the Maclaurin representation of cosine and sine of x are equal to those functions, then all of a sudden we come up with this bizarre and amazing and mystical idea that e to the I x is equal to cosine of x plus I times the sine of x. And this is called Euler's formula. And actually, E stands for Euler. That's where it comes from. Euler starts with an E. E-U-L-E-R. But this is amazing. Not only have we found a relationship between this bizarre, mystical, magical number E and these trigonometric functions that we defined as the ratio of the sides of right triangles, but now we're involving this other mystical, magical number that we invented just so that all of our polynomials would have some root, whether or not they're real or not. We have this number I all of a sudden showing up. This by itself is amazing. But now we could take it one step further, and this should blow your mind. If it doesn't, then you have no emotion. I will just judge you. So if we take this, and I mean, essentially we're taking it that when you take something to the I power, that you can just substitute into its Maclaurin representation. But anyway, I won't go into the details. But I think you can say that this is a pretty reasonable proposition. But what happens if we take something to the pi power, if e to the I pi power? Well, before we didn't have any way of saying, well, what does that mean, taking something to the I pi power? But now we do, because we're saying that these two sides of this are equal to each other. So what happens? Let me do this in a bold color, because it deserves to be bold. E to the I pi is equal to, well, where x is pi, is equal to cosine of pi plus I sine of pi. Well, what's cosine of pi? This is equal to -1. And sine of pi, well, that's just equal to 0. And we get e to the I pi is equal to -1. This is amazing. Or you could also write e to the I pi plus 1 is equal to 0. Once again, amazing. Either of these should make you question your take on reality. because we have the number pi, which is the ratio of a circumference of a circle to its diameter. We have the number e that comes from a continuous compound interest, and then we have the number I, which is you can say the square root of -1, or it squared is -1, and they all come together. This formula right here, it involves all the fundamental numbers in mathematics, but they come from completely different directions. Completely different directions. And although we can prove this and we can say this is true, I'll tell you no one, probably in the history of mankind, fully understands why this is. This is just a glimpse on some type of order in the universe.